In this video, I'm going to discuss alkanes, which, as I've written up at the top there, are singly bonded hydrocarbon chains with linear backbones. And so if that combination of words doesn't really mean anything to you, we will be describing in this video what that means. And so just as a small review from our previous video, I have just sort of looking at how we can put these hydrocarbon chains into this sort of stick model here. And so we have our 3-carbon molecule here, which is completely saturated with hydrogens. And so we see that that will just be something that looks like this, where we know because, again, carbons can never have more than 4 bonds, and unless there is a charge or a free radical, which I won't get into too much, then we know that it has to have 4 bonds. And so we can see that this right here is going to have 3 implied hydrogens to it, since it's only bound to one other carbon, and same with this one. And that is what we see here and what we see right here. Then this central carbon right here is bound to 2 different other carbons, so it has 2 implied hydrogens, which is what we see right here. And so we can also do that with other substituents here. So if we have this amine group here, then that will be drawn like this. So we do actually explicitly put those on there. So it's the carbons and the hydrogen attached to carbons that are sort of suppressed and just implied because of what we know about the way that carbons and hydrogens bond. We can just sort of make that assumption. We just implicitly know about that. And so here we have a glucose molecule, and so this is what it might look like with all of the hydrogens and carbons shown explicitly. But when we draw it with this type of diagram, again, we suppress the C's and we suppress the hydrogens that are bound to carbons, and we end up with something that looks like that. Then if we have, say, a carbon that is completely saturated with these chlorines, with these halogens, then it will be drawn looking something like this, where this carbon here, the C is suppressed, and we will know that it's not bound to any hydrogen since it's bound to 4 other things. So the other thing to notice too in both of this one and this one is that I have the lone pairs suppressed as well. And so that is something that you encounter quite often in these types of drawings. Because again, it's just known that that oxygen, for instance, these oxygen atoms up here are going to have 2 lone pairs. If they are not charged, they will be bound to 2 things, and they will have 2 lone pairs. And same with these chlorines here, is we just sort of know that when it's bound to one thing, it will have these 3 lone pairs, and so those will often be suppressed. And that's just another one of those shorthand things. It makes it easier to draw, it looks less crowded, it's faster to draw it, and just because of the way that we know how these atoms bond and what sort of valence they have, we can just know implicitly what other things are on those that are not actually being shown. All right, and so here we will actually get into these alkanes. And so these are sort of the first 10 alkanes here in their names, which I have over here on the left. This is the naming convention for the first 4. These are the alkane chemical formulas here. So the number of carbons, the number of hydrogens, and this is how they are drawn in these stick diagrams right here. And so we have methane, which methane is just a single carbon with 4 hydrogens, and so it's pretty much always shown like this. So there isn't a stick formula for it, since the carbon is not bound to any other carbons or anything else really. And so there isn't a stick formula for that, because I mean it would just be essentially a dot. But that would, I think, be confusing, since we use dots for other things like free radicals and lone pairs and so forth. So when we talk about methane, you will usually see it like this, or in sort of its 3D structure, which would be something that looks like. So we'd have our H's here, and so we then draw the wedge here for the one coming out of the screen, and then the one going into the screen. But I'll talk about 3D structures more as we go along. Then we have the 2-carbon, which will have just be sort of a line that looks like this. That's called ethane. If it's a substituent on a larger chain, then it's called ethyl, where methane is called methyl. And so we see that we're just adding this sort of YL at the end when it's a substituent on a larger chain. So it goes from methane, ethane, propane, butane, which these four are kind of those are just things that you have to remember, where with the rest of them, the sort of prefixes on it kind of, I think it's the Greek prefixes, but pent, so like pentagram is a 5-sided figure, so pentane is a 5-carbon hydrocarbon chain, hexane is 6, heptane is 7, octane is 8, nonane is 9, decane is 10. And it will keep going. I'll actually show here in a minute some of the other names for things beyond decane. But we see when we get to the propane, we start doing it with the sort of slanted lines like this, where each corner is going to be a carbon here. And so we start with 1, 2, 3 carbons, and we go to 1, 2, 3, 4, and so on, just continuing to add carbons to the end like that. So we see that the formula for the number of carbons and hydrogens is C sub n and H sub 2n plus 2. And that plus 2 comes from the fact that the two n's have 3 hydrogens, where all the middle ones have 2, and so the two n's have 2, or have an extra hydrogen each. And so that's where that plus 2 comes in. And so this, again, is the naming. This comes from Wikipedia here. This is just for the methane through decane here. And we can see that the density is increasing. So these first 4 are in gas. So butane, we see the boiling point is actually 0 here. And so it becomes a gas above 0 degrees Celsius. And so if you get a butane lighter, so it's probably sort of a little bit pressurized in there, you get a butane lighter, you see that it's actually liquid in there, but if you just spilled that out, it would sort of quickly evaporate. Then so over here we see the number of isomers that these have, where the methane, ethane, and propane we see are not going to have any more isomers. Where an isomer, as I will get into in a little more detail here, is just the same number of atoms in the molecule, but it's arranged in different ways. Then we see the density here for after that. These are all liquid, and they increase, but the increase starts slowing down. But the number of isomers starts increasing dramatically here. Then if we go down here, this is for decane and beyond. So we have decane, then 11 carbons will be undecane or undecane, then dodecane, tridecane, tetra, penta, hexa, hepta, octa, nona. Then we get to icosane here, which is 20 carbons. Then this just starts going up by 10. So triacontane, tetracontane, pentacontane, hexacontane, heptacontane. We see the number of isomers starts increasing dramatically. And that's because there are just so many different ways you can start arranging the different carbon atoms. So, binding them to different parts or different carbons and so forth. And so, like I've been talking about these isomers. So what I'm mostly talking about here are what are called constitutional isomers. And so what we see here, so we have this 3-carbon thing with a fluorine bound. And the fluorine can be bound to the central carbon or one of the end carbons. So the number of each kind of atom is exactly the same. The number of carbons is the same, the number of hydrogens is the same, and the number of fluorines is the same, but they can be bound at different places. And so that can actually be true for carbons as well. So I said that the methane, ethane, and propane don't have constitutional isomers because propane is just 3 carbons. So there isn't a different way that you could bind the different carbons together. But when we get to butane, we see that now we can have it like this, or we could have it like this, and then instead of binding this carbon here to that carbon, we now bind it to the central carbon. So that would be an isomer, a constitutional or structural isomer of that. So these other kinds of isomers, so these stereoisomers, are things I will get into in later videos, so we won't have to worry about that just yet. So yeah, structural isomer, where in the IUPAC they call it constitutional isomers, where this is a something we will be running into a lot. So this is just the International Union of Pure and Applied Chemistry, and they are essentially the ones who come up with all these different conventions, in particular these naming conventions that I'll be discussing, well, throughout this video series. It's kind of unfortunate when you're taking this intro level organic chemistry, naming, which is a necessary but kind of not that fun or interesting part of organic chemistry. It's just something you have to deal with. And so the IUPAC, or International Union of Pure and Applied Chemistry, naming, or nomenclature as you will often see it, is what we will be using for this. And so a structural isomer, which is, like I said, or a constitutional isomer, is a compound which is another compound. So this is important because an isomer, even though it might have sort of the same name to it, like what we see down here where we have butane and isobutane, so they have that same butane thing. They are different compounds. They will have different sort of chemical and physical properties. So it is another compound. It's just that we name it similarly because of the number of atoms it has and so forth. So it's another compound whose molecule has the same number of atoms of each element. And so we have this butane here, which is going to have 4 carbons, and it's going to have 2, 4, 6, 8 plus 2, so 10 hydrogens. So this is C4H10. This isobutane, so it has 3, 6, 9, and then the central carbon will have 1 hydrogen, so 10. So it is also C4H10. And so they have the same chemical formula when put that way, but they are different compounds because they have this this difference in the way that they are bound. So it's another compound whose molecules have the same number of atoms of each element. So they'll have this same chemical formula here, but with different distinct bonds between them. And so what we'll see, so it would also be a valid or legitimate way to draw the butane like this, and we'll actually get to that when we get to the stereoisomers. But we see in this, we have just rotated around that bond there. And so we're not actually changing what anything is bound to. And so that is not a structural isomer. That will actually fall into stereoisomers, which, like I said, I'll talk about in future videos, but it is not a structural isomer. It's exactly the same structurally as this one right here. And so it has to be different and distinct bonds between the atoms. And so that is what a structural or constitutional isomer is. All right, and so I'll go through a little bit of this naming stuff. So we have pentane, then we can have isopentane here, and neopentane. When we start getting to larger molecules, we won't see this kind of naming convention. This is sort of strictly for pentane, because as we'll see in larger backbone molecules, so like hexane, that we have a different way of naming these. And in reality, if you saw somebody name this as say 2 methyl 2-methyl butane, that probably wouldn't be strictly incorrect. But we can call this isopentane. So we see that instead of having this carbon here bound to that carbon, the carbon is now bound to this carbon right there. So we've sort of moved it to that carbon right there. And then we have neopentane, which has this central carbon here bound to 4 other carbons right off of that central carbon right there. All right, and so I'm going to move over here, and we'll go through a little bit more naming for some of these more complex molecules. So naming. So, like I said, there are IUPAC naming conventions for organic molecules. And the idea behind these naming conventions is that if you were just given the name of the molecule, you would be able to draw the structure of it just from the name. And in fact, if you're taking sort of a 200 level organic chemistry class, that will probably be, you'll probably see that quite often in like your homework assignments, is given a name, draw the structure, given a structure, write the name for it. And so I have a couple of structures here. So these are octane backbones. And so we can see that because, and I'm going to use a different color here. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So this is an octane backbone, and we have this right here. So this is a CH3 right there, and so it's 2-methyl octane because it comes off of this 2, so it's 2-methyl because we have this methyl group right here, octane. And you might also see it written this way, so methyl 2-octane, so putting the 2 sort of between the substituent and the backbone here. So the methyl here is our substituent, and the octane here is our backbone. And the backbone we always want it to be the longest continuous linear chain in our molecule. And so we see here, now we have 1, 2, 3, 4, and so now we have 4-methyl, so this is our methyl right here, so 4-methyl octane. So it's still up to 5, 6, 7, 8 carbons on our main chain there. So that is 4-methyl octane or methyl 4-octane. And so one thing you'll notice here, and so this is part of the naming convention, you always start from the side that sort of has the most substituents, or I guess if you want to put it in a little bit less of a technical, sort of the side that has the most stuff going on. So we wouldn't start counting from this end and call it, say, 7-methyl octane. We always start from the side that has sort of the most stuff going on. And so this has a substituent on this carbon right here, so we start counting from that carbon right there. And so on here we see we go to 4, but there is 1, 2, 3, 4 over here, and then 1, 2, 3 carbons on this side before we get to our substituent. So we start counting from that carbon right there. And so that is part of our convention here is always starting from the end of the molecule with sort of the most or the largest substituents. All right, and here are a couple more, even more complex things. So on here, we again have octane because we are starting from here. So we have 1, 2, 3, 4, 5, 6, 7, 8 in our main chain here. Then on the third carbon, we have this 1, 2, or you might see it as 1 prime, 2 prime, like that. And so that's an ethyl group. So it's 3 ethyl because we're on the third carbon. We have this ethyl group here. Then we do 4, 6 dimethyl. So on the fourth carbon, we have a methyl group right here. And on the sixth carbon, we have a methyl group right there. So it's 4, 6 dimethyl octane. And so what you'll see is I started counting from this side, and that's because we have this ethyl group here, which is a larger group. So we have 1, 2, 3 carbons to get to this, and we have 1, 2, 3 carbons to get to this. But since the ethyl group is the larger substituent, we start counting from this side right here. And then over here, so this is just a little bit different. So now we have 3 isopropyl, and so instead of having just an ethyl group here, we now have this isopropyl group here, and it is on the 1, 2, 3rd carbon right there. So it's 3 isopropyl. But now I've put this methyl group here, which is on the second one, and then we have this on the fourth one and this on the sixth one. So it's 2, 4, 6 trimethyl octane. So we still have 8 carbons in our main backbone, which is the sort of longest continuous linear chain of carbons on there. And so what you might also find in homework problems in this sort of 200 level organic chemistry is something that looks like this. And so they try to trip you up because we have 1, 2, 3, 4, 5, 6, 7, 8. And you might think, oh, that's an octane. We have this nice linear chain of carbons here, which is 8 long. But what we'll see is that we actually have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we would actually want to start counting from this carbon because this is actually the longest continuous chain of carbon. So we see this one actually has 9 rather than 8. And so we would actually start from that carbon there. So it's drawn this way. You could sort of straighten it out. So if in your head you want to sort of twist around some of these bonds so that you end up with the nice sort of 1, 2, 3, 4, 5, 6, 7, 8, 9, like that, then we would have our substituents. So this is on the third one. So we have a methyl group there. We have an ethyl on the fourth one right there. Then we have methyl on the fifth. We have another methyl on the seventh, like that. So if you wanted to straighten it out so it looked like that, so that we have the 9 sort of in this nice sort of back and forth here. But it's perfectly valid to draw it the way I have it drawn here. And like I said, if you are taking a 200 level organic chemistry class, you'll probably run across this in homework problems, and they're trying to trip you up because they're, you're going to be tempted to start counting from here where we have the nice sort of zigzag going straight across. But we do actually want to go through the largest continuous linear chain of carbons. And so that actually starts right here. So the name for this would actually be 4-ethyl because we have the ethyl on our fourth carbon right here, 3,5,7 trimethyl nonane. So that's our 9-carbon linear chain, so the nonane there. So 4-ethyl 3,5,7 trimethyl nonane. All right, and so then we could try naming this molecule. So I encourage you to pause this video and try naming it yourself before I go through it. But in this case, so we want to count the carbons on our longest carbon chain. In this case, I did just put it in the nice zigzag, so we can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know it's going to be a decane backbone. But now let's look at these substituents. So we have 1, 2 methyls on this 3. We have on the fourth carbon, we have an ethyl. We have an ethyl and a methyl right here. Then on the fifth one, we have another ethyl right there. And so it looks like we have 4, 5 ethyl. So 4, 5 ethyl, then 3, 3, 4. Since these both show up on the 3, what we would do is 3, 3, then we have another methyl on the fourth, so 4 methyl, and then the backbone was the decane, so we put decane. So 4, 5 ethyl, 3, 3, 4 methyl decane. So I actually have the answer over here, and so so I actually missed the tri here. So we should have a tri on there. So this should actually contain a tri. So we see that I actually got that wrong here. So it should be 3, 3, 4 trimethyl. And I mean, you'll see different conventions for like what to put first. So diethyl. So if we want to sort of switch the diethyl and the trimethyl here, that's actually something I forgot when I was naming it up here as well, as we should have had a di up there. So 3, 3, 4 trimethyl, 4, 5 diethyl decane, or you could have 4, 5 diethyl, 3, 3, 4 trimethyl decane on there. But the idea is if you see this name, you would be able to draw these structures. So we could actually do that here. So we know it's a decane, so we could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so we only have 3, 3, 4 trimethyl. So we could do 1, 2 on our 3, and then another one on our 4, then 4, 5 diethyl. So we could do that 4, and then 5, we could put another ethyl there. And so that is actually the same molecule. So instead of starting from up, I started from down over here. And so that's just kind of flipped around, but it's the same molecule. And so you could just take the name and actually draw the molecule from the name, which again is another one of those things you will find in your organic chemistry homework. All right, here is another thing. So these substituents here, so another convention, and so introducing conventions is a big part of this sort of introductory organic chemistry. Putting these R's and R primes here just tells you that essentially there is other stuff on here. So, we could sort of continue on with a hydrocarbon chain, or we could even, we could have other substituents on there. We're just saying that it's just sort of a generic continuation of that. And so we're just sort of zooming in and interested on a substituent on this carbon here. And so we have 1, 2, 3, 4, and so that's butyl. And so when it's linear, we call it N-butyl. If we have 1, 2, 3, 4 in this constitutional isomer here, we call it sec-butyl. And when we have the carbon here, and then sort of 2, 3, 4 going off there. We call it tert for tertiary butyl. So secondary butyl and tertiary butyl. And so this is just another sort of naming convention that you have to get used to. Then we can also have halogenated hydrocarbons. And so again, we start from the end of the molecule that this substituent is closest to. And so this is a butane, and there is a chlorine coming off of the second carbon on it. So we call it 2-chlorobutane. You might also see it as chloro 2 butane. So either of those you might encounter. But this is 2-chlorobutane, so it would be the same if we had a bromine here, so 2-bromobutane. Then we have 2,3-difluorobutane, so we have a fluorine on the second and on the third carbons here, and so we have 2,3-difluorobutane. And so the naming convention for the halogens would continue in that manner. So then here I put some exercises. Again, I encourage you to pause the video and try to draw these structures for these things yourself before I do them. But I'm going to sort of go through these here. So we have 3-methylhexane. So we know hexane is 6 carbons, so 1, 2, 3, 4, 5, 6. We have a methyl on the third, so that would look like that. Then we have 2, 3, 4 trimethylheptane. So we want to draw our heptane. So 1, 2, 3, 4, 5, 6, 7. So that is a 7-carbon hydrocarbon. We have methyls, where trimethyl on the second, on the third, and on the fourth carbon. So that would look like that. Then we have 1,1,2 trichloropentane. So pentane is 5 carbons. So 1, 2, 3, 4, 5. Then we have a chlorine there and a chlorine there, and then another one on the second carbon. So this is our first, second, third, fourth, fifth. We have 2 of them on the first, so that's these 2 chlorines here, and then 1 on the second. Then we have 3,3-dimethyl octane, so octane is 8, so 1, 2, 3, 4, 5, 6, 7, 8. We go to the third carbon, and we have 2 methyl groups on it, so that would look like that. Then we have this 6-tert-butyl 3-ethyl-2,2-dimethyl decane. So we'll start with the decane backbone. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 6-tert-butyl. So we're going to go 1, 2, 3, 4, 5, 6. We have this tert-butyl here. So that is going to look like this. So remember, that is our tertiary butyl. Then we have 3-ethyl, so we go to the third carbon there. Then 2,2-dimethyl, so that is going to look like that. So that is our 6-tert-butyl 3-ethyl 2,2-dimethyl decane. And so those are how we will draw those structures there. All right, so some physical properties we can see for the melting and boiling points of these alkanes. So we're going from methane up to decane, then to undecane, then to pentadecane. Then we have our icosane and our tricontane here. Just the thing to notice is the boiling point and melting point increases for these. And in fact, we can plot that like this. And so we see the boiling point here in orange increases as the number of carbons increases, and so does the melting point. And kind of an interesting thing to notice here too is that the melting point increases as we go from an odd to an even number of carbons more than we go from an even to an odd. And so we get this kind of step pattern going with the melting point. But we see that the melting point increases as we go up in the number of carbons on this. And that will actually have to do with the the van der Waals forces between the carbons. So if we have, if we have a mixture of, we'll call it pentane here. So we have these hydrogens on here, which will have the sort of, transient, these sort of transient partial charges on them as the cloud of electrons moves about, and so we will have these forces going between there. Where then, if we get to say octane, so 2, 4, or 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. We have a lot more places where these sort of transient interactions can happen between these, and so that will cause these to sort of interact more easily, and that's what increases the melting and boiling points for these. So sort of a place where you will probably see these kinds of things in everyday life is in the octane of your gasoline, as we call it here in America, or petrol, as it's often called elsewhere in the world. So the octane rating of your petrol or gasoline has to do with essentially, how much octane is in your fuel. So we have isomers of pentane, hexane, heptane, and octane are the primary constituents of our gasoline or petrol. So they must be able to evaporate since the liquid does not burn as efficiently. So when it's sort of in the cylinder of your engine, you want it to be in a gaseous form when it actually ignites. So when the cylinder is actually moving up, it sort of reduces the pressure and causes it to evaporate into a gas when it actually ignites, so when the spark plug ignites it. And so we don't want any liquid droplets in there, because this can cause what's called knocking here. So octane resists this unwanted combustion really well. And so that's why these sort of higher grade petrol or gasoline, the higher grade fuels, will have higher octane ratings. And you'll also notice that it's often called unleaded. And that's because earlier on, what they did to get rid of this unwanted knocking is they would add tetraethyl lead, which has a structure that looks like this. And so it has this lead here with these 4 ethyl groups bound to it, and that would actually reduce this unwanted combustion. But they have since gotten rid of lead in gasoline, since it causes terrible pollution and can cause harm to people. So that's why you will see your fuel called unleaded, because it doesn't have lead in it. And so the octane rating, it goes between 0 and 100. And so the octane rating of something like heptane has an octane rating of 0, where this here has an octane rating of 100. And so it's actually 2,2,4-trimethylpentane. And so we have a pentane backbone here. So we have 1, 2, 3, 4, 5. Then we have 2 methyls here on the second carbon and 1 on the fourth. So it's 2,2-trimethylpentane. But it's 8 carbons in total, so it's often called isooctane, which is sort of I think that's a non-IUPAC naming for it, but this does have an octane rating of 100. And sort of all other hydrocarbon molecules sort of fall between these two things in their octane rating. In fact, I think pure sort of N-octane, so just the N-octane sort of linear hydrocarbon, is not actually an octane rating of 100, if I'm remembering correctly. All right, and so we can get into the 3D structure of alkanes here. So this is just the 3D structure of methane and ethane. And so we see that this hydrogen is sort of going into the screen, this one coming out. And so we end up with this tetrahedral geometry here. And In the methane, the carbon-hydrogen bonds are 1.09 angstroms. We have 109.5 degree bond angle between these. Where when we get to ethane, because this right here is larger than a hydrogen, it's actually going to sort of push this hydrogen down slightly. And so we actually get a slightly larger bond angle there. And so we actually have what are called inductive effects. And so this carbon here is actually sort of pushing a little bit of, it's sort of adding a little bit of negative charge into this carbon here, which is going to push this hydrogen out slightly. And so we actually get a slightly longer carbon-hydrogen bond there. So the other thing to notice is that, like in this ethane here with the single bond, we have these sp3 hybrid orbitals, and it is perfectly valid to just sort of rotate these around relative to each other, because there's no double bond here that is sort of locking those into any conformation. And so we will actually use what are called these Newman projections. And so that's looking at it sort of from the end. So if we have an eye here, we are looking at our molecule this way. And this carbon right here is what we are showing right there. And this carbon right here is sort of this larger circle right there. And so we can have this in these different sort of conformations here. So when they are sort of perfectly aligned with each other, we call it eclipsed. When they are sort of perfectly staggered from each other, which is why it's called staggered, we call it that. So when they have this 60-degree angle between them, then any other angle that is not 0 or 60, it is called skewed. And so this staggered one is actually the most stable version of it, and that's because there is the least amount of interaction between these different hydrogens on here. And so we can actually look at the energy here, and so these different staggered conformations here have the lowest energy, and so those are actually the most stable form of the molecule there. And in fact, we can do Newman projections for larger molecules. So for butane, for instance, so now instead of hydrogens, we have these methyl groups on here. So now we have the totally eclipsed, which has the two methyl groups sort of back to back like that, and that would be our it would look like that in our sort of stick line drawing rather than like that. So this right here is sort of the one that, well, it would look more like this. So we have our carbon sort of pointing in the same direction. Then you can twist it so that the methyl group is 60 degrees away from it, and this is what is called gouge. Then you can have eclipse. So this one is totally eclipsed, where the two methyl groups are in the same orientation. This is eclipsed, where they're just eclipsed with these hydrogen atoms here. Then we get to this one, which is anti, or sometimes called fully staggered. And so that would actually be our molecule when it's like this. So we are twisting around that bond there, so around that bond there as we go through these. And so this right here would be the anti or fully staggered. And we can see that that the fully staggered is in fact the sort of most stable form of this, where this gouge staggered, this gouge right here is somewhat lower, but the fully staggered is the lowest energy right here. And so that's actually going to be the most stable, and it will be the main form of the molecule that you would actually see if you actually measured the bond angles on these. All right, and so I'll quickly go through a few of these different reactions for alkanes. So the one that you are probably most familiar with is combustion. So that's just taking our hydrocarbon here with oxygen, you add heat, and it's going to make CO2, and it's going to make H2O. So we can look at a couple examples here. So we have this propane here. We add these 5 oxygen molecules. We get 3 CO2 and 4 H2O. We have these 2 hexanes right here. We add 19 oxygen and heat. We get 12 CO2s and 14 H2O. Which you'll notice goes off of this formula of N and N plus 1 here, but that's because we have 2 hexanes, which we need for the stoichiometry of this. And so we are getting sort of doubled on these coefficients here. So instead of sort of 6 and 7, we are getting 12 and 14. Then we have these alkane reactions called catalytic cracking. This is actually used in refining crude oil into petrol or gasoline. So crude oil will often have these much larger hydrocarbon chains, and so you want to break it down into the pentanes, hexanes, heptanes, and octanes of fuel. And so if you do this with H2 heat and a catalyst, you get these alkanes like this. If you do it with just heat and catalyst with no H2, you will end up getting these double bonds in it. Those are actually called alkenes, which we will get to in a later video. Then the last reaction here is just halogenation, and so that's just adding halogens, so fluorine, chlorine, bromine, and iodine onto our hydrocarbons. And so there are different levels of halogenation you can get. So we can take like our methane here plus Cl2, we add heat or light, and we get this single chlorine on here. We can get up to double chlorine, triple chlorine, and tetrachlorine right here. And so that's going to have different stoichiometries of the amount of chlorine we put in here. And in reality, all of these reactions are going on at the same time. If you're reacting methane with chlorine, you're going to get a mixture of all of these, but you can somewhat control the amount of each of these products that you get here by controlling the amount of chlorine that you put in this reaction. And so with fluorine, this reaction is very fast, so that's actually a bit harder to control because it's just going to quickly go to the products, and it's kind of going to not care sort of, what ones of these we end up with, where Cl2, so chlorine and bromine, are going to be a little bit easier to control because they are only moderately fast, and then iodine is actually very slow, and in fact you will probably find that you're not getting much reaction at all with iodine. But anyway, those are just a few of the reactions when we're sort of purely talking about alkanes. When we start getting into cycloalkanes in the next video, and then alkenes, and then start adding other functional groups and substituents on, there are more interesting reactions. But these are sort of the reactions for pure alkanes. But anyway, this video has been kind of going on long enough. I hope you found this interesting and useful, and I will see you in the next one.